A multi-agent system that runs perfectly in a local prototype will routinely break under the weight of real-world production traffic. The issue stems directly from how most standard frameworks manage context. They orchestrate agent interactions using simple while loops or linear execution graphs, maintaining the system's current state in a single, unstructured list of messages held in active memory. As the logic scales up to include parallel subagents executing multiple tool calls simultaneously, those concurrent tasks inevitably attempt to read and write to that single memory list at the exact same time. Under load, this shared memory architecture collapses. The resulting data collision forces the loop into an error state, immediately wiping the active memory. From an operational standpoint, relying on these loops guarantees race conditions and corrupted data. If a timeout or exception occurs mid-flight, the system has no memory of what happened 5 seconds prior. The entire context is lost. To build reliable, highly available AI applications, engineering teams have to abandon simple memory scripts entirely. The workflows must be modeled as formal distributed state machines. This is the exact mechanism LangGraph uses to re-architect agent execution. It implements Google's Pregel Bulk-Synchronous parallel actor model, processing operations over strictly typed communication channels. Moving from an unstructured memory list to a formal distributed state machine marks the boundary between a brittle AI experiment and an enterprise-grade orchestration layer. LangGraph discards the concept of an unmonitored call stack. Execution is instead structured around a persistent heartbeat of discrete, synchronous blocks, known as supersteps. At the very beginning of a sequence, let's call it superstep N, the runtime pauses to inspect the overall state. It identifies every downstream task whose specific trigger conditions have been met by previous data. Once identified, the execution phase begins. Every ready node, for example, a single model turn emitting half a dozen independent tool requests, launches all of its tasks concurrently. Utilizing asynchronous routines or parallel thread pools, you end up with a massive array of parallel execution happening simultaneously. But if all these tasks are computing data at the exact same time, the system needs a way to avoid the memory collisions that crash standard while loops. LangGraph enforces strict isolation. Executing nodes do not write directly to global shared memory. Instead, outputs enter an isolated pending write buffer. This buffer acts as a quarantine zone. No node can read intermediate writes of another operating within that same superstep. This absolute isolation ensures that concurrent subagents cannot accidentally overwrite or corrupt each other's intermediate logic. By buffering these state mutations and holding them in quarantine, LangGraph entirely eliminates the non-deterministic memory failures that plague standard multi-agent loops. Eventually, those isolated tasks complete their execution. The system must then take those quarantined outputs and safely merge them into the global state. This happens at the BSP barrier, a global synchronization point. When tasks finish, they wait at this boundary. Execution completely halts until every single active node has completed its work. To move data safely past this barrier, LangGraph replaces standard Python dictionaries with a specific protocol called a base channel. Standard dictionaries are poorly suited for distributed systems because they blindly overwrite existing values whenever a key collision occurs. If two nodes return a list of sources at the same time, the second one deletes the first. To prevent data loss, LangGraph uses a channel reducer mechanism. Buffered writes pass through a binary operator aggregate. Applying predetermined resolution rules, it cleanly merges conflicting outputs, concatenating independent search arrays into a single list instead of overwriting them. This deterministic conflict resolution ensures it doesn't matter which parallel task finishes first or last. The final merged state will always be mathematically identical. This architectural safety requires a trade-off. Developers cannot rely on passing untyped ad hoc variables between functions. They have to write explicit state schemas and define exact reduction logic up front. The synchronization barrier, paired with these explicit reducers, transforms chaotic, concurrent AI outputs into a perfectly predictable state ledger. Once the state is merged cleanly at the barrier, the runtime takes immediate steps to protect that state against unexpected hardware or network failures. At the end of every superstep, the base checkpoint saver commits a full, immutable snapshot of the entire application state directly to a persistent database. To manage this immense volume of data efficiently at scale, the database architecture relies on a highly specific indexing strategy. LangGraph explicitly avoids standard UUID4 identifiers because their random distribution forces databases to work harder to organize them. Instead, it assigns UUID6 tags, which encode the precise monotonic time ordering in their high bits. Because UUID6 identifiers are strictly chronological, databases can query thousands of historical checkpoints instantly via sequential index scans. The system gains native time travel. Developers can roll execution backward, edit a variable, and fork a new trajectory without altering the original timeline. This allows engineering teams to rewind, inspect intermediate logic, and test alternative paths without wasting compute resources rerunning expensive LLM inferences from scratch. Consequently, crash recovery becomes a non-issue. If an API outage causes a catastrophic failure at step 50, the runtime simply reloads the immutable snapshot from step 49 and resumes instantly. Zero lost context. This checkpointing architecture also solves one of the most difficult challenges in enterprise deployment, requiring human-in-the-loop review for sensitive AI actions. In a typical Python script, pausing to ask for human input blocks the active operating system thread. In a server environment with thousands of concurrent users, blocked threads rapidly exhaust system capacity and crash the application. LangGraph bypasses thread blocking entirely by using a native interrupt primitive that interacts directly with the checkpoint database. When the agent hits an approval gate, it does not hold the system open, it safely powers down. The exact sequence looks like this. The interrupt function serializes the active channels, commits the UUID6 checkpoint, and fully terminates the active process. All CPU and memory resources are immediately released back to the host server. When a human operator finally clicks approve, whether that's 3 seconds or 3 days later, the engine reloads that exact checkpoint, injects the user's feedback directly into the return value of the interrupt, and continues the superstep exactly where it left off. This decoupling of state from active threads also enables dynamic scaling. For tasks where you do not know the necessary scale at compile time, LangGraph provides the send primitive. If an agent ingests a massive document folder, it processes the input and emits a variable number of send packets, fanning out 50 independent tasks across parallel worker nodes. The system processes them asynchronously and gathers results at the next barrier. Because workflow progression relies entirely on the persistent state ledger rather than active system threads, the framework achieves true asynchronous multi-tenant scalability. When you assemble these primitives, the difference between a traditional loop and a formal state machine becomes stark. On one side, you have in-memory loops that are highly vulnerable to race conditions and data loss. On the other, execution flows rigidly from a superstep to parallel node execution to a synchronization barrier, into a reducer commit, and finally into a UUID6 checkpoint before advancing. Because every transition boundary is rigid and logged, system administrators gain total observability. You can track exact token consumption, monitor payloads, and audit state transitions across large fleets of agents with zero guesswork. Achieving this level of reliability requires engineering teams to sacrifice the rapid prototyping speed of plain variables, accepting the strict boilerplate of defining typed dicts and custom channel reducers. But when you are orchestrating multiple foundation models, systems that are inherently non-deterministic by nature, enforcing a deterministic, strictly validated execution environment is mandatory. Robust enterprise-grade AI architectures are not achieved through longer prompts or clever code loops. They are built by applying rigorous, fault-tolerant distributed systems engineering directly to agent execution.